Hello 10thers, welcome to Isha Schools. I hope you are excited as I am to embark on this incredible learning journey together. I am Gayatri and absolutely thrilled to be your teacher. Together, we will unlock your potential and make learning enjoyable and accessible to all. Get ready for the engaging lessons. All the examples and exercises will be discussed along with the board questions and sample papers. Buckle up because adventure starts now. So children, class 10 is a very important class. The first stepping stone towards your future success. Alright, now we will start the first chapter of class 10, which names real numbers. So we will be doing real numbers. Alright, now let me introduce to the contents of this chapter. The first, introduction. Introduction is about what is real numbers. What do you mean by real numbers? Alright, and the next, the first fundamental theorem of arithmetic. Then comes exercise, the first exercise 1.1, which relates to the fundamental theorem of arithmetic. Alright, now the next topic is revisiting irrational numbers. Alright, so we had done rational numbers in the earlier classes. Now we will learn about irrational numbers. How do we prove that they are irrational numbers? Alright, then comes exercise 1.2, which is based on proving of irrational numbers. And irrational numbers are always proved in the method of assumption. Alright, then comes the summary. The summary of everything we had discussed, what all we had done will be told. Alright, so now starts the introduction. Now what are real numbers? Real numbers are all the numbers present in this real world. We are in the real world, isn't it? So all the numbers present in the real world are real numbers. But you know, for everything there is an exception. Similarly, for real numbers also there is an exception. Alright, now what is that exception? That exception is complex numbers. Complex numbers. Alright, complex numbers. Complex numbers. Now what are these complex numbers? Why are they called complex numbers? Because they are imaginary numbers. Okay, they are not real numbers. We imagine that may be the answer. We imagine that is not the real number. For example, I, which is called iota. Iota. I is an imaginary number. The value of I is root over minus 1. We had done root over positive numbers, isn't it? We haven't done under root over negative numbers. So this is an imaginary number. Imaginary number I, the value is root over minus 1, which is not a real number. So except complex numbers, all the numbers, natural numbers, integers, whole numbers, every number existing, even rational numbers existing in this real world are real numbers. So concept is clear about real numbers. All are real numbers except complex numbers. Now, in this chapter, the positive integers are done. Now what are those positive integers? These positive integers we will be doing, and we'll be doing about two very important fundamental theorems. Alright, first is the fundamental theorem of arithmetic, the second is the Euclid's division algorithm. Alright, so these two are very important and the most important things done in this chapter. The whole chapter is based on these two theorems. All right. So now we come to the first theorem, which is Euclid's division algorithm. All right. Now, what is this division lemma? We have done division, simple division earlier, isn't it? What is this Euclid's division? What does it say? It says for any positive integer a, it is always, the Euclid's division is always dealt with positive integers. Okay. Now, for any positive integer a can be divided by another positive integer b. So, how do we remember it? Positive integer a can be divided by another positive integer b. All right. If a is divided by b, all right, in such a way that it leaves a remainder r. So when you divide, children, definitely you get a remainder. Maybe 0, but you get a remainder. So we get a remainder. It leaves a remainder r such that r, now the final condition, this r is always less than positive integer b. It has to be less. This is the Euclid's division algorithm. So I repeat, for any positive integer a, this integer can be divided by positive integer b. Okay, it can be divided in such a way that we get a remainder. It leaves a remainder r. All right, and this r, very important to know, this r is always less than positive integer b. All right, now this is Euclid's division algorithm. So easy to remember, isn't it? All right. So if you remember this map, you will easily remember what is Euclid's division algorithm. All right. Now, this Euclid's division algorithm, if we want to apply in the exercises, how do we apply? That is very important. This is a theorem and it has been said as a theorem. But how do we apply in the exercises? Now, there is a very simple formula which you had already done earlier. If not, you can use it now because this is what Euclid's algorithm says. Dividend is equal to divisor into quotient plus remainder. When we do exercises, I will repeat this, but this is what we should remember while solving Euclid's algorithm. All right? Dividend is equal to divisor into quotient plus remainder. If you go on getting remainders, you have to repeat those steps till you get remainder 0. All right, I'll be doing it again and you can remember that. All right, so this is the first theorem, first division algorithm of your chapter, real numbers, Euclid's division algorithm. Now we come to the next very important fundamental theorem of arithmetic. Now this fundamental theorem you have already done in classes 6, 7, 8 and 9. Very simple, but this is a proper method of theorem which will be applied in this chapter of real numbers. Now, what is that fundamental theorem? Every composite number can be expressed or factorized as a product of primes. Product of primes means the product will be consisting of only prime numbers. And this factorization is unique. Why is it unique? Because it may be in any order and the factors are only prime numbers. Then the prime numbers, the factors may not be in increasing order. They can be in any order. That is why it is unique. All right. Let me give you an example. Suppose I have a number 30. Now, what are the factors? How do you do the factors? A simple short division method. What is that? You always start from the smallest prime number. Alright, start from the smallest prime number. We get 15. 15 is divisible by 3. Then 5. 5 and then 1. So 30 can be expressed as 2 into 3 into 5. Now as we can see, 2, 3, 5 are prime numbers. So this is the fundamental theorem of arithmetic, which says that now 30 is a composite number, we know. So 30 can be factorized or expressed as a product of primes, that is prime numbers. You can take any composite number. Suppose I take 210. Alright, 210, I will use the short division method to find the factors. 1, 0, 5. Now we'll go with 3. 3 3s are 9, 3 5s are. Because the last number is 5, I use 5 as the factor. Then it comes 7 and then 1. So 210 can be expressed as 2 into 3 into 5 into 7. This is the fundamental theorem of arithmetic, where the composite number 210 can be factorized or expressed as the product of prime numbers. So what are the prime factors of 210? 2, 3, 5 and 7. Clear, children? Isn't it? Very good. Now, we come to the examples of the chapter real numbers. We'll do the examples, which will be a basic guide for you to do the exercises. Alright, we will do each and every sum of the exercise, but examples are important as they are the guidelines, the guide for solving exercise sums. Alright, now consider the number 4 to the power n, where n is a natural number. Alright, n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. So what does this actually example say? The question says, so the number is 4 to the power n. If we put any natural number in place of n, after multiplication, the answer should be such that the last digit is 0. Let us check first. 4 to the power 1. 4, not ending with 0. Okay, let me try the other. 4 to the power 2. 16, not ending with 0. Let me try the next one. 4 to the power 3. 64, not ending with 0. Isn't it? No. So when do we know, how do we know? By seeing the number itself, that if we put the natural number n, it will end in 0. The only clue is the factors of the number. Here the number is 4. What are the factors? Factors are, it is a product of 2. 2 and 2. The factor is only 2. So for the digit to end with, the number to end with the digit 0, the factors always have to be 2 and 5. Here it is only 2. We need 5 also. Unless we have the factor 5, the number 4 to the power n cannot end with 0. So how can we prove this, that it does not end with 0? We will write that factor of 4 is 2, not 2 and 5. A number can end with digit 0 only children, okay? Only when the factors are 2 and 5. Alright, only when the factors are 2 and 5, after solving, the number will end with the digit 0. Alright, so this is the key line for this answer. And children, when you go on to solve the sums, please remember the key lines. Why? What is the question asked? Okay, the way of answering also is very important in class 10, and stepwise answering. Every step carries marks, children. Alright. So a number can end only with the digit 0 if the factors are 2 and 5. Since, after writing this, you will write, since the number 4 has only 2 as factor, the value of the number will not end with digit 0. Okay, children? So this is the way you answer. Alright? So now it is absolutely clear. So only if it has factors 2 and 5, the number will end with the value of the number will end with the digit 0. Alright? Now let us move to the next example. Example 2. Find the LCM and HCF of 6 and 20 by the prime factorization method. Now, in earlier classes, you have already learnt LCM, the lowest common multiple, and HCF, the highest common factor. Alright. Now, how do we do by prime factorization method? Now, let us write. Just see, children, how I write the questions and how do I do in the steps. So these steps are very, very important. Each step carries marks. You omit any step, the marks are deducted. So please don't think this is understood. We can do it, it is already done. No, you need to present the answer in such a way that you are explaining to the teacher. Alright? Good. Now the number 6. What are the factors? 2 into 3. 2 and 3 are factors. So it can be made as a product of 2 and 3. 20. 2 into, yes, 2, very good, into 5. Absolutely right. Now, here we want to find the LCM also and HCF also. The first rule for LCM is you take the highest powers of each number. Now here it is 2 into 3, the highest power of 2 is only 1. But here the highest power is 2. And the rest of the individual numbers you will multiply. Highest power is 2 square, then 3, then 5. What is the value? 2 square is 4, 4 3s are 12, 12 5s are 60. LCM is 60. Now comes HCF. As the short form says, HCF, highest common factor, common. What are the factors common between both 6 and 20? Only 2. The common factor is only 2 and no other number is in common, no other factor. So HCF is 2. Alright, so now we write answer LCM is 60, HCF is 2. This is the way we answer. Alright, so this is how we solve the questions in class 10. Example 3. Find the HCF of 96 and 404 by prime factorization method and hence find their LCM. Now they are asking first to find the HCF and then the LCM. Alright. Now here I will give you a formula where the formula says HCF of two numbers, positive numbers A and B, into LCM of two numbers, positive numbers A and B, is always the product of the two numbers, positive numbers. This is a simple formula where we use for this kind of questions. All right. Now, here 96 and 404 are the numbers. Let us first find the HCF and then we'll put in the formula to find the LCM. HCF, the numbers are 96. If the numbers are little bigger, children, previous question the numbers were smaller, so I did it directly. Suppose the numbers are bigger and you feel you may make a mistake. If you feel, otherwise you can do it directly. So we use the shortcut method of division for accuracy. 2 4s are 8, 2 8s are 16, 2 2s are 4, 2 4s are 8, 2 12, 2 6, 2 3 and 3 1. So how is the 96 done as a product of prime factors? 2 into 2 into 2 into 2. How many times, children? 5 2s and a 3. All right. So 2 into 2, 4 into 2, 8 into 2, 16, 32 into 3 is 96. Now take the next number, 404. 404, since the number ends with an even number, I will take 2 as the factor. All right. So first factor, 404, I will take the first factor as 2, 202. Again an even number, so I will do with 2, 101. Now children, 101 is a prime number. Now it cannot be split, isn't it? Okay. The numbers, the product of the primes are 2 into 2 into 101. As we have done already, the common factors we need to see, 2 and 2. All right. No more other factor is in common. So HCF is equal to 2 into 2, that is 4. Now we got the HCF as 4. Let us put into the formula, direct formula. 4 into LCM is equal to 96 into 404. So LCM is equal to 96 into 404 whole by 4. This goes directly 101. So 101 into 96, 96 into 1, 96, 0, nothing, again a 96. Easy. So now what, after solving, don't leave it like that. You are supposed to write the answers separately. What is the question asked? Hence find their LCM. So the last sentence will be LCM is equal to 9696, 9696. All right, children? Great. Now we come to the next example, that is example 4. Let us see if the formula given by me applies to 3 numbers. That was the formula for 2 numbers, isn't it? Let us see if I can apply for 3 numbers, if it agrees, if it satisfies. All right. So let us see. Find the HCF and LCM using prime factorization method. All right. Now let us first find the HCF. HCF for numbers 6. It is 2 into 3, 72. Now as I told you, 72 is a bigger number. Let us use the shortcut method of division. 36, 2, 18, 2, 9, then 3. You don't put direct 9, you take 3 because we need to do with the lowest prime number. So 72 is 2 into 2 into 2 into 3 into 3. The next number is 120. All right, 120. How do we do this? 2, 60, 2, 30, 2, 15, 3, 5, 5, 1. So how is it done? 120, how will we make the product? 2 into 2 into 2 into 3 into 5. HCF, of course, common. 2 is common, 3 common. So what is the HCF? 2 into 3, that is 6. All right. Now, here the three numbers. How do we find the LCM? LCM we need to do directly. That formula does not fit here. All right. It is the formula only for two numbers and not three numbers. Let us see that. Now, LCM. How do we find LCM? As I told you, the highest powers. For 2, here is 2 cube into 3 square. All right. And here 2 to the power cube, 2 cube into 3 into 5. Now for 2 the highest power is 2 cube. Then comes 3. Here the highest power is 3 square. 3 square. And then the numbers are 5. What are the numbers? 5. Only 5 is left. 2, 3 has been done, 5 is left. 2 cube into 3 square into 5. Alright? 2 cube is 8. 8 into 9, 72. Now 72 into 5. 360. Okay, now LCM is 360. So we have found out the HCF and LCM as 360. HCF is 6 and LCM is 360. All right. The formula which I told you does not apply for three numbers. How? Let us see. HCF into LCM is equal to product of the numbers 6 into 72 into 120. Now HCF is 6, LCM is 360 is equal to what is 120 into 6, 12 6 are 72, 720 into 72. What is the answer? 14, 0, 7 2s are 14, 50. The 51840. Here is 51840. What is 360 into 6? 360 into 6. 0, 18, 2160. So not equals to, not equals to. It is not equal to. So this proves we cannot use that formula which I told you for two numbers. It cannot be used for three numbers. It can be only used for two numbers. So this part for this question, this is only to show you I have done. You need not do in the exam. After this 360, you will straight away write the answer. HCF is 6. LCM is 360. That's all. Only this much you will write. This only to show you it doesn't work for. Alright children? So we have done the examples. Is it clear? Of course. Thank you.